In this lesson, we're going to examine entropy in the second law of thermodynamics. Now, when we were looking at heat engines, we saw that heat always flowed from hot to cold, and I said that that's one statement of the second law of thermodynamics, and we're going to look at a second statement of the second law of thermodynamics. So we know, yes, heat spontaneously flows from hot to cold, but that only applies in specific instances. However, you guys would never expect well, think about this. A boulder at the top of a cliff can fall off. It gets jostled. It falls to the ground. All of its energy changes from gravitational potential at the top to kinetic as it falls, and then it smashes into the ground and it essentially becomes thermal energy. A little bit of sound, which causes air particles to vibrate, so that's thermal energy, and the ground will get a little bit warmer, the boulder will get a little bit warmer, and we have more thermal energy. That conserves energy, so it doesn't violate the first law of thermodynamics. But neither would the opposite. If all the thermal energy around a rock sitting on the ground suddenly rushed into kinetic energy and threw the rock into the air, energy would still be conserved. But we never see that happen. So we need another statement of the second law of thermodynamics. And essentially, that statement is natural processes move toward a state of disorder. And disorder is called entropy. But that means we expect a rock to fall and increase the amount of thermal energy, because thermal energy is disordered energy. It's not very capable of doing work. In fact, there's a philosophy out there that says eventually all energy is going to dissipate into the most disordered state. This is heat death. And that means there won't be any pockets of high energy, there won't be any pockets of low energy. All energy will be the same. And that means that the temperature everywhere will be the same, and that means no more work can be done. And so that's like the ultimate heat death of the universe. All energy becomes unuseful. We're not anywhere close to that. We have lots of useful energy around. But we can measure the disorder, the change in disorder of a system. When we do that with a thing called entropy. The second law of thermodynamics can be stated generally as the total entropy of any system plus that of its environment increases as a result of any natural process. That means disorder increases naturally. If you want to order something, you're going to have to put work into it, and energy is going to be required. But naturally, the disorder of an environment increases. Okay? So how do we actually calculate a change in entropy? Well, entropy is given the symbol S, and the change in entropy of a system is given by the equation delta S equals Q over T, where Q is the heat added to the system, T is the temperature of the system, but in Kelvin. So let's look at an example. A 56-gram ice cube is taken from a freezer. In a few minutes, exactly half changes from solid at 0 degrees Celsius to liquid at 0 degrees Celsius. Find the change in entropy. Well, we need the heat that was gained, and we also need the temperature. The temperature is easy. 0 Celsius is 273 Kelvin. But the heat we actually have to find, right? Remember, heat is equal to, depending on what's happening, in a phase change, it's mass times the latent heat. In a temperature change, it's mass times specific heat times change in temperature. We have a heat of fusion because we have a change from solid to liquid. So our Q is equal to the mass times the latent heat. And for water, we have we have 28 grams, which is equal to 0.028 kilograms. And the latent heat of fusion for water is 333 kilojoules per kilogram, or 333 kilojoules per kilogram, or joules per gram. So we're going to go ahead and we're going to take 0.028 kilograms times 333 kilojoules per kilogram, and out of that we get 9.3 kilojoules. Okay? So that's how much heat was added to the ice to make it change from a liquid to a solid at 0 degrees Celsius. We can then take that and use it in the entropy equation. Delta S equals heat added divided by temperature, and we get 9300, right, kilojoules to joules, divided by the temperature in Kelvin, and then 273 Kelvin is 0 degrees Celsius, so divided by 273, and that gets us 34 joules per Kelvin. That's a positive change. So we don't care about the absolute entropy, we care about the change in entropy, and so for this little ice cube that melted, the increase in entropy was 34 joules per Kelvin. That's nice because the temperature was constant. If the temperature isn't constant, then it's a little bit more complicated to do this. We have to look at how heat and temperature are related. But as long as the temperature change is small, we can cheat a little bit and we can use an average temperature. So then we're estimating entropy. So if the temperature changes, we really should use calculus. We'd be finding the area under a curve, but we're going to approximate it using an average temperature. So you'll notice in the last example, we just looked at the sample. We didn't look at the environment. The cup that was in, the air around it, they would also have had an entropy change. So now we're going to take a look at two things. A 50 kilogram mass of water at 20 degrees Celsius is mixed with a 50 kilogram water sample at 24 degrees Celsius. Estimate the change in entropy. All right, well remember delta S equals Q over T. So first thing we have to do is we have to find the heat gained by some and lost by others. So we're going to need to know the temperature change because here we don't have a phase change, we have a change in temperature. Q equals mc delta T. Because we have equal masses of water, we know that the final temperature of these two samples is going to be the same and it'll be exactly in the middle. So the final temperature here is 22 degrees Celsius. Which means our change in temperature is 2 degrees for one of them and negative 2 degrees for the other. So let's go ahead and figure out how much water flows from the hot water to the cold water. So Q equals M, 50 kilograms, times C, the specific heat of water. Since I'm in kilograms, I'm going to use 4186 joules per kilogram, times the change in temperature, which is 2 degrees Celsius. And from this we get 41860 joules. 100. 2 times 50 is 100. Sorry, 2 zeros. 41860 joules. That flows out of the hot water as it cools down, and then it would flow into the cool water as it warms up. So if we want to find the change in entropy, we actually have to find the change in entropy of both samples of water and then add those together. So first we're going to look at the change in entropy of the hot water. And so to do that, we're going to use the heat that it lost. And so that would be 418,600 joules negative because it lost it, divided by its average temperature in kelvins. Now the average temperature of this sample of water was 21 degrees because the final temperature was 22. For the hot water, sorry, that would be 23 degrees. The final temperature was 22. The initial temperature was 24. So 23, but that's at Celsius, not Kelvin. So plus 273 equals 296. So 418,600 divided by 296 Kelvin is equal to negative 1414 joules per Kelvin. So that's the change in entropy of the hot water. So you'll notice its entropy actually decreased. Okay? Is this a violation of the second law? Well, let's see, because we also have a change in entropy of the cold water, and it gained 418,600 joules of energy, but its average temperature is a little bit less. Its average temperature, because it went from 20 to 22, is 21 degrees, and that plus 273 gets us to 294 Kelvin. 294 Kelvin. And now this is a positive change in entropy, and this is 1424 joules per Kelvin. And if we sum these two things together, what we get is 10 joules per Kelvin. That's our change in entropy. Our total change in entropy is equal to this positive 10 joules per Kelvin. So even though the hot water became more ordered, the cold water became more disordered, and since its average temperature was lower, it had a greater change in entropy, which means our overall entropy change is positive. So yes, disorder did increase, and it does follow the second law of thermodynamics.